guys, so this is the 9.1 notes. This should be a lot of review for you from last year. So we're going to start out with Pythagorean theorem. Again, this should be a ton of review. So your Pythagorean theorem, as a refresher, is a squared plus b squared equals c squared, where c is the longest, c is the longest side, also called the hypotenuse. So for this particular problem, we can call our long side our hypotenuse C. We can just call this B for fun, and this one we can just call A. That's fine. So we're going to just plug it into the formula. So we have x squared plus 9 squared equals 24 squared, which means that x squared plus 81 equals 576, which means that x squared equals 495. I can square root both sides just like we did in chapter 5. And I need to rationalize that radical, or that's not the word I'm looking for. I need to simplify that radical by using my factor tree. So it splits into, you can do this a lot of different ways, but 5 and 99, I picked the easy route. 9 and 11, 3 and 3. I have a pair of 3's. That means that I can pull a 3 out. So I get x equals 3 square root 55. That's all that I'm looking for in that problem. On the next page, we are talking about trigonomic ratios. So the biggest thing that you need to know for this is SOHCAHTOA. So the O's stand for opposite, the H's stand for hypotenuse, and the A's stand for adjacent. We're always talking about this in relationship to an acute angle, so an angle that's less than 90 degrees. So we don't do it from the right angle, we only do it from the angle that's less than 90 degrees. And these, we're specifically talking about this angle theta. That's what this little O with the line through it means. It means a theta, it's a Greek letter. So from this theta, we look at the side that is directly opposite it. So this guy right here that I just put the O with. The one adjacent means next to. And the hypotenuse is always the longest side. The hypotenuse will always be the side opposite of the 90-degree angle. So our sine is opposite over hypotenuse. Our cosine, that's what the K stands for, is adjacent over hypotenuse. And our tangent, our TOA, is tangent equals opposite over adjacent. The cool thing is that we have some reciprocal functions, and those are these down here in the second row. We call them reciprocal functions because they're going to be basically flipped versions of sine, cosine, and tangent. So our cosecant, this guy here is called cosecant. It's our flipped sine, so it's going to be hypotenuse over opposite. Our secant is the reciprocal of cosine, and it's going to be hypotenuse over adjacent. And our cotangent is the reciprocal of tangent, and it's adjacent over opposite. I always get confused on which ones go with which, so you just always want to have one S and one C together for the sine, cosine, cosecant, and secant. I always try to put sine with secant. I get confused that way, but you want one S and one C together for those to work out well. Alright, so then we also have these special triangles. This 45, 45, 90-degree triangle comes from a square that we've cut in half. So this side and this side are the same length. So if this one down here is x, it means over here on the side we also have an x. If we use Pythagorean theorem, we would find that the hypotenuse is x square roots of 2. So that's always going to be true. That relationship will always be true for our 45, 45, 90s. We have another special case, which is our 30, 60, 90. These come from our equilateral triangles that have just been cut in half. So if this is a full length, then this would be half of that length. So what we're actually going to call this is we're going to call the shorter side x, and we're going to call this longer side 2x. Again, if we use our Pythagorean theorem then, we would find that the height is x square root of 3. Those are the important pieces that you need for these triangles, is you need to know the relationship of x is the short side, 2x is the hypotenuse, and x square root 3 is the longer leg. All right, so then let's start looking at some actual examples. Here, we are looking at some examples of ratios for our special angles. So again, we're really just using our SOHCAHTOA. So we have sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. And then we have cosecant, which is going to be our hypotenuse over our opposite, tangent, which is going to be our hypotenuse over our adjacent, and this one should actually say cotangent. Cotangent is going to be adjacent over opposite. So then we can look at the angles in our triangles to figure out what would be what. So if we're looking at our 30-degree angle here, for our sine, we want the opposite over hypotenuse. So our opposite's 1, our hypotenuse is 2. So the sine of this first triangle at 30 degrees is going to be 1/2. On our cosine, we want our adjacent, which is the square root of 3, over our hypotenuse, which is 2. Tangent, we're going to have our opposite over our adjacent, but as we talked about in chapter 5, we can't leave radicals in the denominator, so we have to remember to rationalize that. So we're going to multiply it by the square root of 3 over the square root of 3, which would give us 1 square roots of 3, or just the square root of 3 over, and remember that when we're multiplying square roots together, our radicals end up working together and we just can pull out that 3. So we could say that that's the square root of 9, because remember we multiply the insides, or we can just know that the square root of itself is going to be whatever the number in the radicand is. So this 1 over the square root of 3 will rationalize to the square root of 3 over 3. On our cosecant, we are doing our hypotenuse, which is 2, over our opposite, which is 1. That reduces to just 2. Our secant, we have 2 over the square root of 3. Again, we would have to rationalize that. I'm not going to show the work for that one. If you have questions, you can ask me about it in class, but we're just going to have 2 square root of 3 over 3. And lastly, our cotangent is just the square root of 3 over 1, because it's our adjacent over our opposite, which reduces to just be the square root of 3. We can continue this process with our other angles as well. I'll switch colors. So if we're looking at our 45-degree angle, we could go with either 45-degree angle, it doesn't matter. But our sine is, again, opposite over hypotenuse. We'd have to rationalize it. We get square root of 2 over 2. Our cosine is our adjacent over hypotenuse, which is going to turn out to be the exact same as the sine because it's a 45, 45, 90. So square root of 2 over 2. Our tangent is our opposite over adjacent, which is just 1 over 1, or 1. Our cosecant is our hypotenuse, square root of 2 over our adjacent, which is 1. That reduces to just be the square root of 2. Repeats with our cosecant. It's going to be exactly the same because it is that isosceles triangle. And lastly, cotangent, 1 over 1 is just 1. I'll have the 60-degree angles filled in on the note sheet on Google Classroom, but I want you to go ahead and try those on your own. So try and figure out what the 60-degree angles proportions are going to be, or what the ratios are going to be as you are watching this video. Take a moment, pause, figure those out, and then check your answers on Google Classroom. Moving on. going to find the missing side length. All you're going to do for this one is use your Pythagorean theorem. Use your Pythagorean theorem. Do that one on your own. Check your answer on Google Classroom. I know you know how to do that. The next one, this one's a little bit trickier. This is using those special cases. Since this is 30 degrees, we know that this angle up here is going to be 60 degrees because it's a 30, 60, 90. So then we can go back to our relationships here. Our long side, or our hypotenuse, is always going to be 2x. Our shortest side is going to be x, and then our longer leg is x square root of 3. We can take this 8 equals 2x and we can solve it, and we find out that x equals 4. So this side here is now 4, and this side here is now 4 square root of 3. Easy enough. Over here, with our 45-degree angle, we know that the other one's going to have to be 45 because this square makes a 90-degree angle, and all of our triangles, as we learned in geometry, add up to be 180 degrees. So we have a 45, 45, 90, which means that this is x, and this is x, and this has to be x square root of 2. So if we take 6 equals x square root of 2, we can solve for x. We can just divide by the square root of 2 on both sides. These cancel, and then we'd have x equals 6 over the square root of 2. But of course, we can't have a square root in the denominator, so we have to rationalize it by multiplying it by the square root of 2 over square root of 2. So we'd have x equals 6 root 2 over 2, which is going to simplify to be x equals 3 square root of 2. So that tells me that if this hypotenuse is 6, then our legs have to be 3 square root of 2 on each leg. All right, moving on. We have our 6 trigonometric functions. Again, this is going to be very similar to that table that we filled in. Just a couple of things to remember. We're talking about from this angle, so this 3 is our opposite side. This 4, of course, is the longest, so it's our hypotenuse. And then you have to figure out what this adjacent side is using your Pythagorean theorem. So you're going to do square root of 3 squared plus b squared, because we don't know what that is, equals 4 squared. The square root of 3 squared is just 3 plus b squared equals 16. So b squared equals 13, square root both sides, and we know that b equals the square root of 13. I cannot simplify that any further. So with that information, you can definitely figure out your 6 trigonometric values. Again, I will post the correct answers on Google Classroom on the note sheet. So once you try it, look at your Google Classroom notes, see if you can figure it out. Make sure that if you're not sure, you're writing down what questions you have so that when you come back to class, you can ask those to me. All right, this one's a little bit trickier because it doesn't give you the triangle, so you have to draw it yourself. We know that we are going to have a triangle. It has to be a right triangle. The trig functions only work with right triangles. Pick an angle to call theta. I'm just going to pick this one. It really doesn't matter as long as you are labeling appropriately. I know that my sine is part of so that means I have opposite over hypotenuse. So opposite of my angle, my theta, I need to have the square root of 3, and my hypotenuse has to be 4. Just like on the last problem, you need to use your Pythagorean theorem to figure out what this missing side is. Figure that out, and then you need to find cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. Try those, try to figure them out, and then check your answers on Google Classroom. Next. cosine, or angle. Okay, so these are probably the toughest part of this section. You are looking at your relationships here between your angles and your sides using your sine, cosine, tangent, secant, cosecant, cotangent. For these, I usually only use sine, cosine, and tangent just because they're a little bit easier to find. But if we're looking at this angle, since we have it's a 40-degree angle, on these you cannot use your 90-degree angle for your sine, cosine, or tangent. It's not going to work. It has to be an acute angle. It has to be an angle less than 90 degrees. So looking for my 40-degree angle, I have my adjacent and my hypotenuse. So that means that I would need to use cosine. So cosine of 40, or 40 degrees, is going to be the adjacent over hypotenuse. Now I just have to solve for x. So I multiply both sides by x, and I get x cosine 40 degrees equals 5. Divide by cosine of 40. And I get x equals 5 over the cosine of 40. This is something that you're going to have to plug into your calculator. It needs to be on degrees. Make sure that you are checking for that it's in degrees. Hang on, somebody's calling me. How do I pause this?